Um, so we're going to continue with the talks, very important aspects of data science. So again, you are relieved of any computational aspect, but I don't know, maybe Dr. Hardin may add some flavor in there, but that she will talk about that. So before we start, I'll just read introduction of Dr. Johan Harden. She is a professor of mathematics and statistics at Pomona College. She completed her PhD at UC Davis in statistics. Her current research includes developing robust methods for high throughput data, and she has an active undergraduate research group. She seeks to find ways to modernize the statistics curriculum, including co-authoring the online and its completely free introductory statistics textbook, Introduction to Modern Statistics. So you can check it out, especially those who need a statistical aspect. When not working with students on her research, she loves to put on her pair of running shoes and hit the road running. So without any further ado, I'll hand over to you, Dr. Hardin. It's all yours.
Great, thank you so much. It's really my pleasure to be here. Okay, so let's see if this share screen works. All right, and so hopefully you can see only just my first slide there. Is that right?
Yeah, that is right.
Perfect. Okay. So thank you for having me and that nice welcome. My name is Jo Harden. I teach at Pomona College. It's an undergraduate institution and in California. So I'm all the way on the West Coast. Today I'm going to talk about ideas of objectivity and, data science as an objective, like the algorithm is the, the truth or whatnot, and how do humans play a role, and what do we think about when we think about data being involved in the model and whatnot. So anyway, this is an XKCD comic that maybe some of you have seen, and it's just a joke about how, in the university, everything is political except math. But, I'm going to argue maybe that math and data science and statistics, those are all quite political as well. Okay, before we really get started, I have a couple of just acknowledgements here. So first of all, I have to move the little videos. Okay, first of all, I want to just do a land acknowledgement and recognize that this is where the original people of Los Angeles County, so that's where I am. These are the groups of people who lived in this space. And I want to recognize the systemic and institutional systems of power that have oppressed Indigenous people, and that many of those same systems are in place today to continue to marginalize those with less power. And a lot of the things I'm going to be talking about today are about systems of power. So, one other acknowledgement is about me. So I'm white, as you can tell. I'm straight, I'm cisgendered, I'm able-bodied, upper middle class, educated, maybe even overeducated American. So besides my gender, I have basically every privilege imaginable. And I just want to recognize that I'm working to do work that, or my efforts are to do work that can really dismantle a lot of those systems of power and privilege. But, I also recognize that I come from a place of privilege and I can't always see that privilege, right? So that's, what some people have called a privilege hazard, that it's hard when you have the privilege to see everything that's going on. So I just, give you that space to call me out on things that you might think that I'm saying that's inappropriate or even wrong. So please do. And then just, because I don't like to wait till the end, I want to just tell you what the spoiler is for this entire talk, that computer algorithms, they can't exist without humans making many choices along the way. So we are intimately involved in every piece of data science, every piece of AI, every piece of machine learning. So, I don't think any of you would say this, but there's lots of examples where people think, oh, it's just the algorithm that is, causing this. It's not actually any of my biases, right? And also, a second point here that algorithms are often based on data, and that means they're going to reproduce patterns in the data. And as we all know, most data sets are biased because they represent differences in power dynamics across racial and gender and many other lines, right? So when we say, oh, it's just the data, well, we don't want to reproduce the data. We don't want to reproduce these systems of power that we know are problematic. So that's what I'm going to try and talk about through a bunch of examples, and also through kind of understanding some of the machinery that goes under the algorithms and the data. Okay, so what is an algorithm? An algorithm is just a set of instructions for solving a task. So let me demonstrate two algorithms here, and these are not necessarily the types of algorithms that we're going to talk about for the majority of the task. But the first algorithm is called a bubble sort. And as you can see, what it did was it sorted the pixels into rainbow order using an algorithm called bubble sort. And this second one over here is called merge sort. And it does the same task, but differently. Right? So again, the idea that we're trying to get to a truth, or we're trying to get to an answer via a series of steps, that there's choices we make. In this particular case, I made a choice about whether I wanted to use the bubble sort or the merge sort to get to the end point. But again, there's an algorithm, there's a series of choices, and there is no capital T truth. But I'm not here to talk about sorting pixels. I'm here to talk about data. Oh wait. There we go. I'm here to talk about data, right? So I'm interested in algorithms on data. And I'm also just recognizing that data comes in lots of different forms. Data could be images, it could be numbers, it could be text, it could be all sorts of links to various information. And kind of thinking about, okay, how does data play a role in the algorithms, and what is data? How do we use that data? I also want to point out this idea of data exhaust, that we are just, constantly giving the world data about ourselves. So, for example, I wear a smartwatch, and so, I'm every second, I'm putting out exhausting data about, my number of steps and my heart rate and various other things from my watch. But there's many other things, right, that are coming out of this data, and recognizing that that we don't always know where the data is coming from, right? Where the data is coming from and how it's being used. Okay, so in that vein, this is where I live. I live in Claremont. That's where Pomona College is. And let's say I wanted to go to Santa Monica. Google has an algorithm, right? It's an algorithm for figuring out what the best route is to from where I live all the way to Santa Monica. And they do this through a combination of models, right? So coming up with, whatever it is, whether it's something, straightforward like a linear model, or something more complicated like a convolutional neural network, they're using some kind of algorithm, but they're also using that data exhaust, right? They're using information from phones, right, that are sending data exhaust information to Google, and letting them know that, hey, this portion of the freeway is quite stopped up. All right, so so like I said, I'm gonna go through a handful of examples here, and this is not one of them, the mapping directions algorithm. But the first example is a hypothetical one. And I think it really helps us understand how models can mimic systems of power without any sort of nefarious behavior. So I got this example from someone named Aaron Roth and his blog. So that's the URL below. I think you have my slides. So all the links to all my resources are at the bottoms of almost every slide. And that's all available for you, I think, on your GitHub repo. And again, this example is really about bias it's about bias and reflecting systems of power without any nefarious behavior. So let's get into it. So let's say that there's a group of individuals and they have talent, and their talent is normally distributed with a center of 100 and a standard deviation of 15. Okay, so that just means that, you know, they're kind of like plus or minus 30. So some people have talent as low as 70, some people have talent as high as 130, right? And it kind of ranges mostly between 70 and 130. And for each of these individuals, their grades and their SAT scores are centered at their own individual talent. So if my talent is 93, then my grades will be centered at 93. And again, we're not using grades on a 4.0 scale. We're using them on a scale of, you know, whatever. They could go all the way to 130 or whatever. And same with SAT. We're just pretending they're all on the same scale here. So like my talent is 93, my grades then, you know, are anywhere between 93, again, plus or minus 30. And my SAT score, same thing. My SAT score is going to have sort of a baseline of 93, but depending on if I have a good day or a bad day, or I happen to know a particular question, or, you know, I'm particularly exhausted that day. So each individual person gets these three measurements. And colleges want to admit students that have a talent above 115. Okay, so the goal of this is to identify, the goal of this algorithm that we're going to talk about is to identify students that have a talent which is above 115, but the college only has access to grades and SAT. And you see that grades and SAT are centered at the true value of the individual, but there's a lot of noise. There's quite a bit of variability associated with each individual's grades and SATs. So what we're going to do is we're going to run a linear regression on some training data, and the training data has talent known. And we're going to find a model which predicts talent based on grades and SATs. So once we find that model, that will then be our algorithm. And we're going to choose students for whom we predict their talent to be above 115. Okay, so it turns out there are two populations of students, the reds and the blues, and the reds are the majority of the population. So the 99% of the students are red and 1% of the students are blue. And so now what I've written here in blue is very key. It's the first key element that we need to consider. These groups of students are exactly the same when it comes to talent. They come from the same population. So there's no bias with respect to who is the blue and who is the red. They have the same grade distribution, SAT score, talent, all of that, because they're coming from exactly the same population. But there is one difference. The blues, they have more money. And as you know, it's expensive to take the SAT. So the blues get to take the SAT twice. And they get to report the highest of the two scores. So what happens is that, and I'm going to show you the results here in a second. What happens is that taking the test twice results in a small but noticeable bump in the average SAT score of the blues and compared to the reds, which kind of makes sense, right? If I have a score of 93 and I take the SAT twice, well, my SAT, you know, one time might be a little above my talent and one time might be a little below my talent. And of course, I'm going to only then record the higher one. That's what I'm going to send. Okay, so again, here's another key insight. the value of SAT, the variable, right, that we're collecting, it means something different for the reds versus the blues. They're just fundamentally different variables for the two groups of people. Okay, so let's see what happens. So here is a scatter plot, and this is grades and SAT scores, and I'm trying to show that there's nothing really going on here. Oh, sorry, no. Sorry, no, there is something going on here. Sorry, that the blues have a slightly higher bump. I'm not sure how obvious it is in this picture, that the blues have a slightly higher from that interior sphere there, that the blue one is just a titch shifted above the line as compared to the reds. All right, so we've got grades and we've got SATs, but remember, SAT means something different for the blues. They're just a little bit higher. Which, you know, is not that big of a deal if we fit two models. So if we fit two models, then we can notice that the coefficient on SAT is slightly different than the coefficient, the coefficient on SAT for blues is slightly different than the coefficient on SAT for reds. Okay, so we're saying SAT means something different. So I'm going to try to predict talent based on the SAT for the red students, SAT and grades for the red students. I'm going to try to predict their talent. And then I'm going to do it again. And I'm going to try to predict trying to predict talent based on the SAT and the grades for the blue students. Okay. And as you would expect, you get a slightly different model. And when I then try to predict, assess my prediction, I notice that there's nothing kind of wonky about this plot. So we see that the kind of the proportion of blues in the upper right quadrant, which represents the true positives, right? So those would be people whose talent is above 115. And who we predict to be above 115, right? These are the people who we get correct, right? They have a prediction of above 115, and they also have an actual talent above 115. Okay, those are the people. It looks like the proportion of blues out of all the blues and the proportion of reds out of all the reds is about the same. And similarly, you know, over here, these are going to be my false negatives. A false negative would be, hey, I have a talent above 115, but you didn't predict me above 115. And then in the top left here, those would be my false positives, right? So I don't actually have a talent above 115, but you're predicting me to have a talent above 115. But regardless, there doesn't seem to be any discriminatory behavior going on here. And we can actually quantify that by saying, you know, what is the true false positive rate, or what is the estimated false positive rate and the true positive rate. So again, you know, the true positive rate is up here and the false positive rate is here, and the error rates, they're not sort of fundamentally different. The variability we see in these numbers is due to my simulation, right? To get actual precise numbers here, we'd want to simulate, you know, many more students, or maybe simulate a bunch of times. But these numbers, this variability here is just kind of within simulation error. So far, so good. No bias baked in, same populations, we're all set. But that's not what happens, right? We don't have a model for blue students and a model for red students. In fact, in a lot of situations, it's illegal to do that. So, you know, there's laws against using protected classes, and protected classes are race and gender and age and ability, right? Those are protected classes. And there are laws against using those protected classes with housing, jobs, credit, loans. College is a little bit different. Sometimes there's a little bit of leeway there with respect to using these protected classes as a criteria for getting into college. Although that's, I don't know, that might be changing as well, but whatever. The point is that generally that's not what we do, right? We fit one model. We fit one model to the entire data set, and we use that single model. And certainly that's true for something like credit, right? For credit, it's just like everybody goes into that bowl and we just, get your credit score out. It's very much a black box. And you'll notice, if you remember back a couple of slides ago, that the coefficients actually look much more like the red model than the blue model. And that's because the red class is the dominant class. And so, they're the ones that are driving the optimization process and the least squares regression. So if we fit a single model, and then we ask ourselves, how did we do? Now, what you can see, and again, I don't know how obvious it is here, but you can see that there's these blue points shifted up. So you can see there's kind of more blue points at the edge of the red, cigar shape here than there are blue points down below. That these blue points have kind of shifted up a little bit. And so what do we end up with? So this is the plot, or the table output from the original observations. And this is the true positive, false positive rates from the single model output. We end up saying, hey, more of my blues who should go, right, who really have a talent above 115, more of them are actually getting into college. And similarly, a much higher proportion of the blues who shouldn't be, that's this little quadrant over here, the false positives, they are also getting into college, right? So what has that happened here when I use that single model, but the feature distribution is different? Then the blues don't fit the overall model as in the same way that the reds do. So what did we learn here? We learned that, when two populations have different feature distributions, that learning a single classifier will fit the bigger of the two populations. All right, so it's this dominant class behavior that allows the model to understand what's happening in the dominant class much more clearly than it understands what's happening in the minority class. And we know that in this particular example, I've done it in such a way that it feels very discriminatory, but it can be either to the benefit or the detriment of the minority population, right? In this case, in this example, it was to the detriment of the minority population, but it could have been to the benefit of the minority population, depending on what the situation is. And the point here is that there was no human bias, either on the part of the algorithm or the data gathering process or the model that was chosen. There was no sort of explicit bias, but this well-intentioned fairness, like I'm not going to be involved at all, I'm just going to let the model do it. It keeps us from understanding sort of what's happening, what's going into the data, and what's what the output is, right? So how is this model sort of differentially impacting people? Okay, so that was my first example, and I'm going to pause for a second and ask people to put, if possible, in the chat, just kind of a reflection on what does this example make you think of? Are there any other variables that have feature distributions which are different across classes? Are there any ways that you've seen in your experiences that that maybe there are discrepancies in sort of who has access to different things. Insurance premiums. Okay, great. So insurance premiums might be something like, in terms of the feature distribution, I'm trying to think of, and you can clarify if in the chat if I'm wrong, but sort of different neighborhoods have different characteristics, and sort of maybe what you're measuring within a neighborhood might be fundamentally different. Yeah, great. Other examples? Anybody else? You guys can do it. Later, I'm going to make you get into breakout rooms. So this is the easy contribution. Healthcare treatment options. Okay, great. So insurance, healthcare treatments. Give me one more. Somebody else though. Somebody else give me one more. It's easier to do this in a classroom, because when you're in a classroom with real people, then there's this awkward silence that students really hate. Granting loans based on credit scores. Exactly. That's a great one, right? So, you know, income versus wealth are two huge differences that are across all sorts of marginalized lines. So loans based on credit scores. And another example, regional settings, right? So how people, how we measure variables in across regions. I mean, even things like, you know, natural disasters across regions, right? So, you know, I live in a place where the issues that we come up with are earthquakes and fires, right? Those are our natural disaster problems. But a lot of people live in places where it's more hurricanes or, you know, other types of things. So there's lots of differences there. Awesome. Okay, you guys are great. Thank you for contributing there. All right, so next up I have just a very short video. So this video was taken, it was a couple years ago now. This was at Martin Luther King Day event in 2019. So this is Martin Luther King Day 2019. And this is Ta-Nehisi Coates. Some of you may know who Ta-Nehisi Coates is, who is an author and activist. And he's interviewing Alexandria Ocasio-Cortez, who's actually who this is. Y'all are looking at me like, that's not Ta-Nehisi Coates, that's Alexandria Ocasio-Cortez. Anyway, and so he's interviewing her and she's talking about algorithms. So let's just give us a listen.
We look at, you know, IBM was creating facial recognition technology to target, to do kind of crime profiling, or you see over and over again, whether it's FaceTime, they always have these racial inequities that get translated because algorithms are still made by human beings. Right. And those algorithms are still pegged to basic human assumptions. Right. They're just automated. Mm-hmm. And automated assumptions, it's like if you don't fix the bias, then you're automating the bias. Mm. And then that gets even more dangerous. Mm.
Yeah. Okay. So what she's talking about is that, you know, if we have this perspective that we are, that we're doing something sort of unbiased because it's the algorithm, what we end up doing is making an algorithm, oh, right. Ta-Nehisi Coates is a professor at Howard now. I knew that. That's awesome. I love that connection. That's fantastic. Thank you for pointing that out. That we make it more efficient and we make it faster and we make it worse, right? So some of these algorithms, you know, you might argue that they're the same bias as the sort of the existence, right? The just kind of like people stereotypes, okay? But the problem, you know, one of the big problems with reinforcing that sort of existing stereotype or existing biases is that you make it faster and more efficient and affect more people. So this particular person is like making fun of her and making fun of this conversation and saying, like, how can math be racist? And this tweet sort of blew up and people were like, yeah, it can be. So really people rallied back against this idea and says, what we're talking about, these bigger things are really, really problematic in terms of systems. Okay. So to move on to facial recognition software, as Alexandria Ocasio-Cortez was talking about, this is one of the really the hot button issues in a lot of different venues with respect to data science and social justice. So I just have a ton of headlines here that are within the last 3 or 4 years. Facial recognition telling creditors whether you're worth being lent to. That people, it's becoming a bigger deal because we're using it more. Police facial recognition software backed by Homeland Security. But then there's a backlash against it. San Francisco bans facial recognition software, an article about the racist history behind facial recognition. Okay, so there's a lot that, this is way beyond just, your Apple phone and your ID to your Apple phone. This goes back a long time, these really important issues. So somebody who was arrested at 14, then all of a sudden her photo is in a database. And, more recently, these two articles, this is just under a year ago, November 8th, 2021. And then this one, November 5th, 2021, that Facebook is shutting down its facial recognition software, citing, these concerns. A lot of the concerns have to do with policing. I think I have one more. But then on the other side is, how else is facial recognition software being used, right? So this is just a few months ago, identifying people who have passed away. So, so let's dig down a little bit into some of the issues that come up when we're talking about facial recognition. So again, it's not just some kind of magic that happens, right? It's actually an outcome of human intervention. So humans have to participate in lots of different ways. So what kind of model is being used? So I put here, are they using convolutional neural networks? What's being optimized? So for those of you who do know a little bit about neural networks, it's you put something through a layer, through many, many layers, and then at the end you have a loss function or some kind of, optimization, and you can optimize the accuracy or the false positives or the false negatives or something even more complicated. What data are being used to train the model? That's huge. Where a camera is placed, what data is collected, who are we collecting data on? What types of parameters go into the model? So how many layers, if we are talking about a neural network, how many layers go into it? What are some of the, other sort of block sizes that go into those layers? What is the cutoff for a match, right? When we talk about, yes, it was successful, it found a match. That's not a yes or no question usually. It's on a spectrum, and we have to decide, okay, yes, this is a match. Yes, this is, or no, it's not. Who's paying for these algorithms? Who's buying them and using them, right? Where is that money coming from? And what is that money supporting, right? So what is the goal of that money? That's another huge one right there. All right. So again, this is a few years ago, but the Amazon was really pushing their facial recognition software to different police officers or police whatever stations, LAPD, whatever that's called. And there was this serious backlash that's saying that there's not enough oversight, that we don't understand what's going on and we don't understand how it's being used. and that it's not about making it better necessarily, but there's sort of underlying issues. So, so now I'm going to talk about two studies that were done to really kind of help us understand how facial recognition software is problematic, and how it's, you know, how it can, again, represent systems of inequality. So this first study was done by Joy Bulamwini and Timrit Gebru, and what they did was they took 1,200 individuals from 3 African countries and 3 European countries. So the individuals were all members of parliament, and they were chosen, the countries were chosen both to have sort of, you know, as much of a polarity in skin tone, as well as countries where there was good gender representation across the parliaments. So there were as many women in parliament as men. So to have a database that had, you know, a broad spectrum with respect to both race and gender. And so what you're seeing here are just some example images, you know, of darker skin tone and of lighter skin tone. And then in the middle, these are sort of composite images, you know, so these two here are sort of composite images of all of the Finnish parliamentarian women and the parliamentarian men. And then these two are these composite images of, you know, all the Senegalese parliamentarian men and the Senegalese parliamentarian women. So just kind of an example of what their data set looked like. And they put these observations through some off-the-shelf classifiers. And they said, okay, how well do I classify this person as just in this, on these 2 binary axes, so dark-skinned versus light-skinned, and female versus male. And these are the classifiers here, and we're measuring something called positive predictive value, an error rate, which is 1 minus that positive predictive value, as well as the false positive rate and the true positive rate. And I've tried to put these all here so that you can kind of have that. And what I want to point out is that the light-skinned males have very low error rates. And the dark-skinned females in particular have very high error rates, and the dark-skinned males as well. So the true positive rates, you know, are much lower here for the dark-skinned males. And you see this kind of, I've circled in red to draw your eye to kind of the most extreme ones, but you see it across the board that the male light-skinned males are far and away easier to classify, or easier for the off-the-shelf classifiers to classify, particularly as gender, but also, you know, getting into that group. So, you know, why does this matter? I mean, you know, lots of things. There's policing issues, of course, but just a story here that this individual, I actually don't know what the race of this individual is, but he received a letter from the DMV saying that his driver's license had been revoked, and he hadn't had a traffic violation in years, and he was like, why is this being sent to me? And his image had been automatically flagged by a facial recognition algorithm. And it was designed to scan through millions of state driver's license looking for potential criminal false identities. And that they had determined, the algorithm had determined that he looked sufficiently like another Massachusetts driver and that there was foul play involved. So the motor vehicles was unsympathetic. And they said, you know, again, this is that like bias that we're really fighting against here, is that they bring up this idea that they're like, no, it's the algorithm. Like when he called, he's like, no, this isn't me. Like, I didn't do anything. They're like, sorry, it's the algorithm. There's nothing we can do. It's your burden. Right? The onus is on the individual. And some of those other examples you gave, like, you know, with credit scores or premiums. Like for you to call State Farm and say, this isn't cool, like my rates are too high, you're discriminating against me. Like it's the onus is on the individual to prove to State Farm that there's racial bias, or to prove to, you know, the university of whatever state that there's this, you know, systematic oppression with respect to SAT scores. And right, so it's a tremendous amount of work for individuals, and they're really being you know, the burden is being put on people, which means that nothing's going to happen, right? Individuals don't have power to fight against these systems. And that the DMV, or they call it RMV, the RMV, argued that protecting the public outweighed any inconvenience to the very few people who would be wrongly targeted, right? Those false positive versus false negative rates. And when we look at what Bulamwini and Gabru did, we think, yeah, but who is going to have this happen to them more often, right? This particular misclassification issue is happening more to people of color and to women. So we are systematically reinforcing those wrongs that already exist, and making it even harder for people who are already marginalized to navigate the system. Okay, so one other study that was done, this is by the National Institute of Standards and Technologies, NIST, which is actually kind of a cool place if any of you are thinking about doing statistics and data science as a career. NIST is like a very cool, it's a government organization, but it's a very cool place to be a statistician and just kind of think about things like, how do we measure things, and you know, how does the government kind of you know, stay accountable. And their study was not done on trying to predict gender and skin color. Their study was on doing actual matching. So more akin to the individual who had the incorrect match on the DMV record. So the data sets that were used by NIST were mugshots, so from police agencies, application photographs from immigration, visa photographs, and border crossing photographs. So, you know, these data sets were coming from sort of government organizations. What else do I want to tell you here? Yeah, so the data sets were collected for authorized travel, immigration, or law enforcement purposes. And they were able to process almost 20 million images, and with 8 million different individual people. So about 8 million people, 20 million images, and they used 180 commercial algorithms from 99 different developers. All right, so as opposed to the Bulamwini and Gabru paper that really looked at 3 different facial recognition software, NIST was looking at you know, close to 200 different algorithms, 200 software, facial recognition software programs. And so I'm just giving you a really high level of their results. So it's exactly what you would expect, that the false positives were you know, high in West and East African people and East Asian people, those matches, and that they were lowest in Eastern European. So, right, so a false positive would be like the DMV guy, right? So you're being matched with somebody who's not you, and that's lowest in Eastern European people. With an interesting caveat here, that a few of these 200 different algorithms were developed in China, and the effect is reversed, where the lowest false positive rates are on East Asian faces. So that kind of makes you think, what is it about the algorithm? What were the choices that went into that algorithm that made it good for a particular type of facial structure, color, whatever it is, right? And what makes it harder for a different type of facial structure? Out of the law enforcement images, the highest false positive rates were in American Indians. This is all quoting from them, so this is their language, not mine. And also elevated rates in African Americans and Asian populations. Also higher in women than men, and elevated in the elderly and in children. They also reported on their false positive rates and said that false negative rates are higher in Asian and American Indian individuals. Okay, so we're seeing the same type of reporting in this follow-up study that says, you know, hey, there's discrepancies, you know, these algorithms that come off the shelf, they really impact different groups differently. So I want to just point out two groups that are doing interesting things here. And the first is thinking about loss functions. So again, a neural network or any other, you know, a random forest, a linear model, you know, a support vector machine, whatever it is that you're using for your algorithm, it takes the data in and it does a bunch of things. And then it tries to think about that output, and it tries to think about, okay, how can I get that output to be as good as possible? What's the best sort of prediction that I can do? Well, the word best isn't well defined. You have to say best according to what metric. And so a really common way is to say, I want my prediction, that's why I hat, to be as close as possible to my, this would be for training data where you knew the outcome. So as close as possible to my known outcome in my training data, according to squared error loss. So right, here's your squared, here's your error loss. The loss is the whole thing, right? So it's the difference, the square difference. But you could imagine doing something with absolute values here, right? So that would be called absolute loss. So the prediction would be as close as possible to the known value with absolute values. And then there's a bazillion other ones, right? There's what you decide to optimize at the very end. I mean, it's like the literature is vast in terms of thinking about that. And so the paper I've put here, it's a little bit more technical than I'm going into in my talk, but this paper this is a talk, but then they have a follow-up paper. So Gentrick, they're talking about using a loss function that maximizes a local optimization. And in particular to control with respect to the imbalanced data. And it's interesting because it's not totally clear to me that it won't have the same problems that I spoke to when we were talking about reds and blues with respect to laws and policies which protect classes. So laws and policies which say we're not allowed to predict, we're not allowed to build our models with respect to protected classes. But I think there's something to be said for imbalance that would, you know, allow us to kind of get away from particular demographics and focused more on, you know, how do we, instead of looking at sort of global, you know, average squared error loss, how do we kind of look at subgroups? And maybe those subgroups are determined by the data instead of determined by the demographics. And so that's the work that this group is doing. So kind of thinking about, okay, how do we change this optimization algorithm? How do we think about a better process that would have false negative rates and false positive rates that were more clear across, or that were more similar across different demographic groups, I guess. Okay, and one other project that I'm going to bring to you today is that we can thwart the algorithm. So this this group, this is out of the Sand Lab at the University of Chicago. They have an algorithm called Fox, and what they do is they put these little pixelated, pieces, I don't know, pixels into an image, and then they put them out into the world. And what happens is that these tiny pixel level changes are invisible to the human eye, but they result in a process we call image cloaking. So what you do is you cloak all of your images through just an app on your phone. Every image you take goes through this cloaking process. And then when you post them to social media, or, give an image to the newspaper because you won a fancy award or whatever it is that could end up on the internet that could then be used for identification of you, then the algorithm can't identify you because of these little blemishes of the images that are there. And so they have a bunch of pictures on their website when they're describing all this, and clearly, you can see that to the human eye, there's no way to distinguish which one is the cloaked image and which one is the original image. And there's a question in the chat. Can there be inherent bias in the data itself? Absolutely. So I'm not sure if this is exactly the question, but let me say something, and then you can see if I've answered the question. But one of the big issues, which I referred to with the algorithms that have been designed by data scientists and individuals in China, is that the data that's going into the model is driving it, is teaching it, right? And so what the actual training data look like is super important to what the tool is going to look like, right? The tool is going to only reinforce or predict, or rather, I won't say only, but the tool is going to best predict whatever it has been trained to do. These aren't magic. They're trained using data and using decisions made by humans along the way. Do you want to clarify and say what other kinds of inherent bias you mean there? Or we're good? Okay. Okay, so go, yeah.
Yeah, I mean, what I meant here, in the data collection is maybe the data, the planning, everything is great, is well intended. But could there be an inherent bias that if maybe a data scientist is not able to break things down to certain levels, you may not be able to identify that bias?
Yeah.
I mean, let me say this, something that could, let's say, be as a result of Simpson's paradox kind of thing.
Yeah, sure. I think there can be paradoxes. I like you said, Simpson's paradox, where different aspects to the data, for example, like thwarting the data here, but there might be something about it that, for example, one of the quintessential, undergraduate image recognition tasks is to differentiate dogs and cats. So you get lots of images about dogs and cats, and you have to, come up with a way to, build a classifier. But the thing is that most images of dogs are taken outside, and most images of cats are taken inside. And so sometimes your classifier can simply be a classifier that's picking up on lighting and sort of background, grass versus couches, and that could be a reasonable classifier in terms of the accuracy rate, but a terrible classifier in terms of distinguishing between, whether the image is a cat or a dog. So I can see things like that, right? So like the images themselves having something going on with them that really has nothing to do with who the individual is or whatever it is that you're trying to predict, but something else. Yeah. Okay. So now I have a task, and I'm hoping you guys will do this for me. I want to put us in breakout rooms just because I have one more example. It's the shortest example, so hopefully it'll go quickly, but I do have one more example. But before we get to that example, because this has been a long talk, I want to put you in breakout rooms, and I want to, and so maybe I can just do it. Hold on. Can I just do this? I think maybe I have control. Breakout rooms. Do we even have breakout rooms? I don't have breakout rooms in this Zoom.
You should have control as the co-host.
I have control. I do have control. I just don't have breakout rooms. Do you have breakout rooms on yours? It just doesn't have, it has mute, video, secure participants, chat, new, share, pause, annotate, remote. I wonder if maybe it's because I'm sharing. I don't know. All right, we don't have to do breakout rooms. Okay, I'm not going to do breakout rooms, but now you have to answer this. So how about if we just unmute or text? So I need at least like 5 answers. Should facial recognition technology be banned? Or if you say no, you know, in what ways should it be restricted? So let's get some contributions here. Feel free to unmute yourself.
So I'll unmute and talk a little bit, and hopefully you can hear me okay.
I can, thank you, yes.
So while I think everything that you mentioned, there are of course pros and cons to anything in life. But I think we can focus a lot on the benefits, and I don't think we should ban it. One of the reasons I am in my program, I'm looking to see how can I use facial recognition to improve how teachers teach. So if you can look at a student's face and correlate their engagement, I just think the benefit of having a resource like that outweighs the cons. So I just wanted to throw that out maybe to help us start the conversation, but that's my initial thought.
Oh, I love that example. Thank you so much for sharing that. Absolutely. Absolutely. And I think there is, maybe correct me if I'm wrong, but I've seen some research on, maybe this is exactly what you're talking about, like how often a teacher or how long a teacher will spend making face contact with, maybe this is on Zoom or something, with different demographics, like with boys or with students of color or whatnot, that you're seeing differences there, that some of that just eye-to-eye contact is different across those. And that's a really important thing for us to be cognizant of.
Correct, yes.
Yeah. Great example, thank you. What else? Somebody else give me an example, or what's your thinking on this?
Well, can I share my thought?
Please.
I appreciate the positive aspect of what facial recognition technology can do, but on the downside, if it's related to like the outcomes, like that might involve criminal activity, of course we want to identify someone who's a perpetrator and harming society, but the margin of error, and then, you know, it just turns everything into a police state, which is not healthy for society in general. So this is not an easy question. And maybe we have to go through classifications on what gets used for facial recognition technology and not.
Right. Or maybe, yeah. So, and when I think you say classifications, maybe what you're saying is there are some industries for which it could be acceptable, and some industries
yes.
for which it could be a positive thing.
Yes, or different, I guess maybe that's where NIST could come in too, is, you know, different criterias for what the use is for.
Right. And there's a chat, it says facial recognition should be banned because facial expression is subject to cultural interpretation. That's really fascinating too, right? So there's issues of recognition, but there's also you know, for example, when we were just talking about the education use and eye contact and whatnot, eye contact may or may not be what we're going for. Or if you're using it to say, you know, how often is somebody smiling, or how often is somebody, you know, frowning or shutting their eyes or whatever, that those are very cultural things. And so putting our cultural judgment on what the expectations are related to the facial recognition software complicate the matter even more. Absolutely. Great. How about one more? One more comment.
If I could go ahead and chime in real quick. I do believe there's a lot of like pros and cons to facial recognition, and I think ultimately that it shouldn't be banned. However, a lot of restrictions should definitely be put in place just to make sure that in a situation where you do have potential drawbacks, we can have regulation that, you know, has a better chance of restricting those drawbacks while optimizing those benefits. Because we do live in, like, you know, a relatively like militant state, like, or a policing state. So there's definitely a lot of opportunities for facial recognition to be used poorly when it comes to like identify individuals for whatever that case may be. Of course, there's a lot of like instances in which, like, you know, that would allow processes in terms of persecuting people to be expedited when, you know, that's necessary. So I definitely do think there are benefits and cons, but it's really a question of making that analysis and putting restrictions in place such that like we're only seeing the benefits and minimizing, you know, any misuses or any like cases in which anything could go wrong.
Right, great, thank you so much. Yeah, and I think it's my very last slide. I don't know, for those of you who yeah, for those of you who actually have my slides, but I think that there are more and more calls for exactly what you're saying, that we need to understand what's going on. We need to put you know, posts around this, guides around this, you know, to really help practitioners, people who are using this, understand what the consequences are, understand what the problems are, and really you know, create structure that that will help you know, restrict that it's not just used in because I think it is used kind of in nefarious ways. Okay, last example here. I want to talk about something called the Stanford Open Policing Project. And so this comes out of the Stanford Computational Policy Lab. And they have been working hard through, oh gosh, I'm blanking on what it's called, through, there's I'm totally blanking. I didn't write it down. It's when you go to a jurisdiction and you say, I want that data, and you that people will give you their data, that it doesn't just exist in a publicly accessible form, but Freedom of Information Act, that's what it's called. They've gone through the Freedom of Information Act to get information on data sets, on police, on traffic data sets and crime data sets. And so this I'm going to talk about a couple of things that this group has done, and some work that I've done sort of with the database. It's an amazing, fantastic database that you should all you know, play around with. So these three images here are images of Nashville. And the left-hand side is just the residential driving age population, and it's colored by the blue points are white, the orange points are black, the green points are Hispanic, and the red points are other. And the middle here is where traffic stops happen. And so what we see here is that the white residential areas have very few traffic stops. And that the density, the majority of the traffic stops are happening in the areas where the people of color live, right? The residential people of color, the residential areas, including more densely populated people, individuals of color. And what we see over on the right-hand side is where non-moving violation crime happens. Okay, so this is just saying, oh, hey, the traffic stops are more closely aligned with the crime than they are with sort of residential. And so you wonder where the cause is, right? So is there a causal mechanism, or is there an association that we could understand with respect to the what's happening with the traffic stops? And what this group found through a series of looking at the data in interesting ways is that Black drivers were stopped more often than white drivers, even within other zones, right? So across the way. So that's this picture right here. Sorry, this picture. Every dot here says is a police zone. What, I don't know how those are defined, but there's a police zone. This is all Nashville. And so within that zone, the number of Black stops per 1,000 people plotted next to the number of white stops per. So even within every single zone all over Nashville, except for a few down here, there are more Black individuals being pulled over. And there are differences in violation rates. Oh, okay, sorry. So the question is why? Why do we see these differences? And so it's possible that this is what I'm trying to say here is why is this happening? What are sort of these causal mechanisms? And we don't know for sure, but it's possible that that there are differences in violation rates, right? So, we could make an argument that Black drivers are disproportionately more likely to have broken taillights. Okay, it's possible that there are differences in enforcement, right? So this would be your implicit bias. It's possible this, third bullet point here is possible because, police are just more likely to pull over Black drivers. It's possible there's some heterogeneity in these zones, or it could be some combination of factors. And this article just did a great job of laying out the what was happening and what we were seeing and what those connections were. And this idea of they found no relationship between the number of traffic crimes and the number of traffic violations and more serious crime. And so they were trying to debunk the idea that extra policing of these traffic incidents, non-moving violations, would lead to less crime, because that's sort of the argument. One argument that could be made was, oh, we're doing these traffic stops because we're trying to cut down on crime. But what the Stanford group found was that there is no association between extra policing and reductions in crime. And so, they brought their report to this is the Metropolitan Nashville Police Department, and they reduced traffic stops by roughly 75% and did not see an associated rise in serious crime. So this is kind of a positive outcome of looking at, racial disparities, in this case in traffic. And something similar happened in LA, that the larger database that is across, I'm not sure how many states. It's not every state, but it's something like 37 states. So they have traffic information, both the highway patrol level and also lots of individual city level traffic states. And through these 100 million traffic stops, they found, as expected, that Black and Hispanic drivers were routinely searched on the basis of less evidence as compared to white drivers. So they found a bunch of different things, but in all the directions that you would expect. And so there was a report out. So they worked with the LA Times. So this was an investigative journalism project that was done with the LA Times and the Stanford Policing Group. And the LA Times broke this. So this is October 8th, 2019, that LAPD searches Blacks and Latinos more, they're less likely to have contraband. And then October 13th, 2019, so just 5 days later, story about LAPD agreeing to drastically cut back on pulling over random vehicles over racial bias concerns. So over the concerns that happened here. So, you know, who knows where this will go? This is maybe just words, but maybe not. So again, this is an example of a situation, a data set, and an effort towards using information about racial disparities to make changes, to make systematic changes. And so just really briefly to end here about some work that I've been doing. This is a really just brief foray into some of my work. The thing about this database is it has quite a bit of missing information. So a lot of the variables will not have data on them. And so what my group is interested in is whether there are fundamental differences between traffic stop observations with high missing and low missing. And so, you know, how do we understand it with respect to things like race and time? And really, most importantly, are the missingness trends going to render any of the results unreliable? Like even those LAPD and Nashville results, like what happens when you kind of incorporate missing information in particular ways? What's the change in the actual results? So what we found here is this is just a metric that we came up with. It's not anything, you know, well-defined or, you know, well-known in the literature or anything. This is the stop missingness rate, and it's just the number of unrecorded variables over the total number of variables. And what you see is interesting. So this is, you know, Iowa statewide versus Kansas, Wichita, Kentucky, Louisville, that you see over time that there's these really sort of interesting, drastic differences in how much of the data is missing. And if you're in Nashville, right, you're like, oh, well, that's like 1% versus 8%, maybe not that much. But in Iowa, you're talking like 30% of the data is missing. And we also looked at it, interestingly, for some of these data sets, we looked at day versus night. So how does the missing, like this one right here, again, it's not huge percentages, but it's interesting to think about why are the variables, you know, why is there less information being collected sort of systematically, you know, during the day versus overnight? You see some different patterns. And then the last thing that my group has looked at a little bit is when race is not recorded. So these traffic stops have race for the vast majority of them, right? They say they don't say the name of the individual, but they say the individual's race and their age, and then sort of why they were pulled over, whether there was contraband, whether I guess first, whether or not they were searched, and whether there was any contraband found, some other information, the time of day, various things like that. And again, a lot of that information is missing. It's not all complete. And so one of the things that I've realized is that in some jurisdictions, the race of the individual is determined by the officer who is pulling the individual over. So they don't even ask you, or necessarily, I don't know why they wouldn't look on your driver's license, but there's some policy briefs that say that the race is supposed to be recorded by the officer to their knowledge of the race of the individual, which brings up all sorts of, you know, sort of bonkers ideas. But anyway, so what we've looked at is this is about being searched, and this is comparing individuals, their odds of being searched if they're Black, the odds of being searched if they're white, and the odds of being searched if they're no race, right? If there's a missing information with their race. And then we compare, you know, this missing group to the odds of being searched if you're Black, and the missing group compared to the odds of being searched if you're white. So if the points lined up with, you know, the vertical line at 1, we would be saying that this number here, that the NA people were kind of like the white people, and you know, if the odds were at the horizontal line of 1, we would be saying the NA people were kind of like the Black people, you know, for in terms of being searched. And we don't really see that at all. What we do see is that that being below the line says that the odds of being searched if you are white is lower than if you are Black. So really, we're just kind of reinforcing some of those ideas that that we've seen before. That certainly that if you're, and the size of the dot represents the size of the metropolitan, or the size of the database. That if you're Black, you're more likely to be searched than if you're white. And so we're still investigating this. Okay, so just a few take-home messages here. What can we do? You know, what this is all like, I feel like it's a terrible talk because it's so depressing. But you know, what we need is for all types of people to be at the data science table. And we especially need Black and brown people. So the more Black and brown people we have at the table, the more these ideas just get brought up and get talked about. We need data that doesn't replicate existing inequities, right? So kind of really being careful about data sets that we bring to the algorithm, and making sure that those data aren't, you know, just what we want to replicate, because more often than not, the data is terrible because society is terrible. The more we can work to find metrics that minimize error rates for marginalized communities and not just that minimize total error, the more the model will be successful at understanding what's happening for marginalized groups. And we can work against pervasive and problematic algorithms by using adversarial methods like that Fox algorithm I told you about. So some good news is that both the Senate and the House have introduced bills regarding automated decision-making process, and so putting some of those constraints that we've talked about onto the use of these algorithms in particular ways. These particular bills are enforced, recognize any sort of institution that's enforced by the Federal Trade Commission, the FTC. So they wouldn't have jurisdiction over companies like nonprofits and insurance, and certainly not over policing, but they would have jurisdiction over, you know, just companies like Amazon. This bill would, among other things, provide baseline requirements that companies assess the impacts of automating critical decision-making. It would require the FTC to create regulations providing structured guidelines for assessment and reporting. And require the FTC to publish an aggregate report on trends to establish a repository of information where consumers and advocates can review critical decisions that have been automated. And last, I just, you know, I think about Jurassic Park a lot when I'm thinking about this, and you know, we're so concerned when, as data scientists and like as students, like, okay, I've got to make a really good algorithm model. You know, I'm so concerned about whether they could. They didn't stop to think if they should. And just really focusing on this need for human values and fairness, even at the cost of efficiency. And with that, thank you so much for having me. It has been a joy to be here, and I appreciate all the contributions you've given along the way.
Yeah, hello, Dr. Harden. This is a great presentation, very informative, and we thank you so much for making time to give us such very informative presentation. So at this time, anyone has any questions, comments, feel free to ask them. You can speak them out, or you can put that in the chat area. Any questions for Dr. Harden? Yeah, looks like there isn't any questions for you, Joe. I'll just ask one question. I'm very interested in the traffic stop data example that you gave, and then you're coming up with this SMR or total for stuff missing.
Yeah.
Metrics over there, because in one of your last, you were talking about what metrics can we come up with? I think that, yeah, exactly. So my question is, the denominator there, the total number of variables, how is that determined? Do they have, if the corp stop you, are they conversant? Do they aware of the things they need to check on the individual? How do they come up with the total number of variables?
Yeah, that's a great question. Maybe I'm gonna stop sharing. The database is fantastic. And again, I encourage everybody to go check it out. So here's the database, and what I want to point out is, I think if I just go here, is that the states and the different jurisdictions, whether it's, you know, the state patrol or the individual cities, they collect really different information. So, you know, again, I don't really know in terms of the Freedom of Information Act, how the researchers, you know, who are involved in this project, whether, for example, this stop location was in there and it was just hard to access, or whether it wasn't in there, or what was going on. But you know, it's kind of interesting to notice that there is no uniformity with respect to even just within a state, right? I mean, this is California, and it's like all over the place in terms of what's being recorded. And there's some states and some state patrols where there's a lot recorded, and then there's some where there's just hardly any information recorded. And I don't know how that is determined.
So there could even be variation within a state, is maybe from county to county.
Yeah, but then the value that we're collecting is, you know, sort of, once we know that these are the variables being collected, how many of them are missing in the, I don't think I can.
On an individual.
Yeah. How many are missing on an individual? Exactly.
Okay.
That's right. That's right. Yeah.
All right. Any further questions for Dr. Hardin? Okay, so if there are no further questions, then thank you so much, all of you, for coming, and thank you, Dr. Hardin. The second part of the presentation, which was supposed to start 12:30 on EHR use of element and use of electronic health record, we are not going to have that talk because the speaker informed me last night that for some other personal reasons, they couldn't make it. So, which is not too good, but at least it's good for you. You're going to have a longer day to rest today. So again, thank you all for coming. We are going to continue next week with another module, and then all of you have a great weekend.
Thank you.